All right, so let's look at the following example where I'm going to be showing how to use the chi-square test to test for independence on the two categorical variables displayed or represented in this current given table right here. All right, so let's now spend some time understanding what the table is presenting for us. And then from there, we should be able to identify the categorical variables and as well as to get into the actual question of the testing hypothesis problem. So in this table, it represents a sample of 1,000 people. And we want to study the political point of view of any person in this sample right here. And of course, being people, we can break it down into two different genders, male and female. So the columns here organize the political point of view for any person. So say within this sample of 1,000 people right here, some people believe in the way of the Republican Party. And so that is their political point of view, which is one among the other point of views. Some people believe in Democrats. So they consider themselves as Democrats. And some people can be independent with the two political parties. And so now as far as recognizing a categorical variable, I can see that being a Republican or being a Democrat or being independent, meaning the neutral from any of these, or even any other political point of view that's outside of these three categories being listed here, then these are all just different values. So these are all values of, and now I can officially name our variable here. So we can name the variable representing all of these as political point of view. All right, and this political point of view here is a categorical variable, and allow me to use a shorthand writing cat here is for categorical variable. All right, and so for any person in our sample, that person in the sample can consider himself or herself to be a Republican. The same person's political point of view in our sample can be a Democrat, or the person's political point of view in our sample can be an independent person, meaning neutral from any of these two major political parties. And so that's, now I have just pointed out that the three columns here are different values of one categorical variable that we have recognized. And now back to the table itself right here. So now looking at the rows here, we have two major values here, being either a male or being a female. And both of these two values belong to a categorical variable that we can name that as gender. So here on my board, I can now see that on the rows here, being male or being a female are the values of, we can name this variable over here. How about genders? And it's a categorical variable. So anyone from our sample here must fall into one of these values of the gender's categorical variable, because any one of us as a human being has a gender. And so after observing the two-way table and recognizing for ourselves the two categorical variables existing in our two-way table, then we are taken to the following question. So at significance level, so alpha once again is indicating significance level. So at significance level 0.001 is the sample as a given table, of course, showing strong evidence that political point of view and genders are dependent. So let me talk a little bit about what it means by dependence in our table. So let me now swing back to my table on the computer screen. So just like the experience we have learned through the general lecture along with the example there, then now anytime we're trying to prove dependence from a given table, we're not specifically pointing to any specific dependence, because according to the way how it's worded, the question is only asking us to prove that two variables are dependent. And dependence only means that there must be some kind, and again I'm repeating, dependence here we're only trying to prove that there must be some kinds of relationship relating between the two categorical variables existing here. So for example, there must be some way that political point of view is related with a specific gender you're in. So for example, we can observe here and see that now if we focus our attention to the male gender over here, then it looks like the most, according to the three entries found in this row for the male gender, then it looks like the within the male, then it's the most of them are the Republican. So we want to find out whether it is true regarding that way for all other tables, that anytime it comes to male, then we always have most of the males in our sample to be Republicans. So that's one way of saying that the two variables are dependent. And in another way of saying, if we're looking at the female gender right here, it looks like in this table, most of the females are in the Democrats. And so outside of this table, is this true for all other tables? Or it's only like this in this table, where the highest number of female is in for Democrats? So if this is true for all other tables, then that's another way of how we can see dependence. And as I said, there are many different ways of how we can recognize dependence in a two-way table, or the dependence between the two categorical variables. And so back to the question here, is the sample showing strong evidence that political point of view and genders are dependent? So being dependent here, we're just simply trying to prove that there has to be at least one way of dependence going on, or at least one relationship that can be recognized between the two categorical variables. But we won't be pointing out which way is the dependence going to be, or we're not going to point out which relationship is existing in the table here. So we're only going to look at the general look at the dependence. And before we proceed any further, I have to admit that after hopefully detailed enough explanations of the steps found in the general lecture of mine, along with the examples being done there in the general lecture, and here in this particular example, I am going to start speeding up the step, as I'm only highlighting the steps. And so the first thing we need to do, as usual, is to identify the two hypotheses. And again, clearly, because the way of how the question is asking, it's a testing hypothesis problem. Is a sample showing strong evidence that political point of view and genders are dependent? So this is the statements we're trying to prove, but the question overall is the kind of question that brings us into testing a hypothesis. So our first responsibility is to identify the two hypotheses. And so learning from the general lecture, now I can first tackle down immediately with H1, the alternative hypothesis. And so the alternative hypothesis here should say that political point of view that's one categorical variable that we recognized. And the other categorical variable, how about genders? So political point of view and genders, these two categorical variables are dependent. So we just directly copy and paste the statement that we're trying to prove from the question, and we copy and paste and put that right here in our H1. And so in that way, once we have recognized our H1, the alternative hypothesis, now H sub 0 will come out easy. Political point of view, in gender, or independent. So notice the two statements, or the wording makes it look almost identically the same, but now if we're reading a little more closely, the two hypotheses are always the opposites of each other. And so once we have easily identified our alternative hypothesis H1, then H sub 0 is simply just the opposite way of arguing it. And that's the whole logic, again, of testing a hypothesis. We want to come up H1 with H1 here as a counter argument to H sub 0. So these two are always statements that are arguing against each other. And so now once we have identified our two hypotheses, then the first step now, as pointed out in the general lecture, our first step now is to be finding, so I'm going to be finding all expected counts. And this is the part where I am going to start speeding through the process right here, because we will be having a lot of expected counts waiting for us here. For example, right here in our table, we have 6 entries outside of those in the total column and the total row right here. There will then be 6 expected counts to calculate for. So I have to start speeding up the process here a little bit. And so now, in row 1, column 1, my expected count is going to be, and now quickly let's have a look at the table before I'm really proceeding further. So row total for row 1 and column total for column 1 are here. And then I'm going to pause it for a little bit so that viewers would have a complete view of the table. And feel free to take a screenshot of the table here, because I won't keep switching back and forth any longer. So now expected count for row 1, column 1 is going to be 400 as a row total for row 1. I'm going to multiply with 450 for column total for column 1. And our sample size here in this case is 1,000, as we have already learned. And so we will be getting the expected count here. Calculation of mine showed 180. Then in the same row, row 1, column 2, now I'm advancing over to calculate expected count for row 1, column 2. And similar work is now done here. Row total for row 1 is again 400. I am going to multiply with column total for column 2, which is also 450. And we're dividing that by 1,000 as the sample size in our total of the sample. And so this calculation here again gives me 180 as my expected count. But this is, so it happens to be the same expected count with the expected count back in row 1, column 1, but it's just a different meaning. Expected count for row 1, column 3, which is the last entry on row 1 right here, is going to be 400 for row 1, row total, multiply with 100 for column 3, column total. And I'm dividing that by 1,000. And calculation here gives me 40. And of course, any viewer viewing this video, or even my students, feel free to pause any of my steps right here in this video to double check with my calculation here. Now we are ready for row 2. So expected count in row 2, column 1 is found by 600 for row 2 total, multiply with 450 for column 1 total. And again, that product is divided by 1,000, our total sample size. My calculation came out 270 as the expected count that happens in our entry row 2, column 1. And now let's look at expected count for row 2, column 2. Row total for row 2 is 600. Column total for column 2 is 450. We take the product of those two totals and divide that by the total sample size, 1000. So calculation came out being 270 again. But this is the expected count for row 2, column 2. Then we are now at the last expected count. Expected count for row 2, column 3. I have 600 for row 2 total. I'm going to multiply with 100 for column 3 total. And the product there I am going to divide by 1000. My final calculation came out to be 60 as the expected count for the entry in row 2, column 3. And so after the calculation, I highly recommend doing this as a habit anytime we're doing chi-square tests for independence. I produce the exact same table with the original one. So this is our original table. These are the observed counts. But as I said, I produce a separate, completely different table with the same total row and the same total column. But these are the expected counts that I put in these inner entries right here. So anyone viewing the video here can double check for my calculation and find out whether I have put the values, the calculations in correctly. But so this is the expected count for row 1, column 1. This is the expected count for row 2, row 1, column 2, and so on and so on. So this is again my table with all expected counts given here. And so now that means we are done with that step, finding all expected counts. So after getting that step done, let's now move on to the next step by calculating all components, or this is for components values. Okay, so let's get all components. And so just like that, I am going to speed up the process in the calculation here. Components in row 1, column 1 is 200 is observed count in row 1, column 1. Subtract 180 being the expected count in row 1, column 1. Square the difference there and divide it by 180. My calculation came out to be 2.22. The actual final value was a lot longer than this, but unless being specified otherwise, I will always round to 2 decimal places. But make sure you watch out for your own rounding requirements for component values in any of your problem that you're doing. So here, throughout this example and many other video lessons on using chi-square test for independence, I will be using two decimal places for component values. So now let's look at components value for row 1, column 2. Observed count there is 150. Now we're going to subtract 180, the expected count there. Then square the difference and divide it by 180, the expected count. My final calculation came out as a whole value, 5. So this is the component value for row 1, column 2. Now let's calculate our component value in row 1, column 3. Observed count there is 50. We're going to subtract 40, the expected count. Square the difference and divide it by 40. My calculation came out being 2.5. Now let's calculate components value for row 2, column 1. My observed count there is 250 minus expected count there 270. Square the difference and divide that by 270, the expected count in the same entry. My calculation came out as a decimal in 2 decimal places, 1.48. And again, I have mentioned that throughout all of my video lectures about chi-square test for independence, I will be using 2 decimal places for any component value. But make sure you will watch for the rounding requirement in any of your problems that you are doing. Now let's calculate components value for row 2, column 2. The observed count there is 300. We're subtracting the expected count in the same entry, 270. Square the difference and divide it by 270. Final calculation gave me 3.33 in 2 decimal places. And again, I'm using 2 decimal places here, but make sure you are watching for your rounding requirements in each problem that you're doing. Now we're at the last components value, components on row 2, column 3. Observed count there is 50. We're now going to subtract 60 as the expected count. Square the difference and divide it by 60, the expected count in the same entry, row 2, column 3. My final calculation in 2 decimal places came out to be 1.67. And again, I have rounded to 2 decimal places, but viewers and students who are learning from this video lesson must watch for your own rounding requirements on each problem you're doing out there. And so now I have created another table where I recorded all of my component values in all of the corresponding entries here. So this was our components value for row 1, column 1, and this was our component value for row 1, column 2, and so on and so on. So these 6 entries here in this table of mine on the computer screen show the 6 component values that we have calculated. So now we have had step 2 completed, calculating all components or component values. So now let's advance to step 3. I am going to be calculating our chi-square value. And so chi-square here is calculated by summing all components we have found in step 2. And so again, let me display the table on the computer screen right here. And now after a little bit of time for any viewer to have the table observed carefully, then I'm going to swing back now to my writing board and ready to add. And so 2.22 is our first component, row 1, column 1, plus 5, the components in our next entry, row 1, column 2, plus 2.5, the components in our third entry, namely row 1, column 3. Now I'm going to add to the components in row 2, column 1, 1.48. And then I'm going to add to the components value we found in row 2, column 2, 3.33. And I'm going to add with the last component value, 1.67, in our row 2, column 3. Final calculation of mine gave 16.2 as my final chi-square value. So this chi-square value throughout all of my video lectures, I will be rounding to 2 decimal places, unless being specified otherwise, depending on different examples. But throughout all my video lectures, I'm going to be rounding chi-square to 2 decimal places. And in this case specifically, we're down to only 1, simply because just the way how we add these values. But again, viewers and my students are on your own responsibility to watch for rounding requirements in each different little problems assigned. And so now that we have had our chi-square calculated being 16.2, and again, just like how I have explained at the end of the general lecture regarding testing using a chi-square test for independence, then these are so far the consequences from accepting the H0 statements, which stated that the political point of view and gender are the 2 independent categorical variables. And so these are all the consequences. And now we have done up to this step right here, calculating our chi-square value. And now along the way, but not exactly a formal step, the degrees of freedom for the current table we're using. Since there are 2 rows, I'm going to go 2 minus 1 and multiply with 3 minus 1, as there are 3 columns. And so number of rows minus 1 times the number of columns minus 1. Our table here has the final degrees of freedom 2. And so now we are ready for setting up step 4 right here. Step 4 is to calculate the final p-value. So p-value for anytime we are running a chi-square test is set up as following. We want to find the probability that among all chi-square values out there, we'll find a chi-square value specifically greater than. So here I'm again using just like how I explained, just how I pointed out in the general lecture, that we will always be using a right tail inequality like this. So we want to be greater than or equal to the specific chi-square that we have already calculated. So 16.2 is here. So that's the setup for our, that's the symbolic setup for our p-value calculation. But now to get that p-value really calculated, we need to use some technology right here. So on my TI-83 and 84 calculator, I am going to hit second variables, which will bring up my menu for all distribution functions in statistics. And I'm going to look for option that says chi-square CDF right here. Okay, and so now for TI-83 calculator users or early TI-84 calculators, then the command will be printed directly on your home screen instead of showing the menu as you have seen earlier on my computer screen. So this is what TI-83 users will see, the command being printed directly on screen right after you call your chi-square CDF command. And now back to the calculator that I'm using right here. This time the lower, I'm going to use the chi-square value that we have now calculated, 16.2 for the lower. And as I have explained in the general lecture, then the upper will be an indefinite upper end. So I'm going to leave that as 1E99. And in case you're not familiar with how to enter that E, 1, and then E is right above that comma key right here, 1E99. And then we are looking at degrees of freedom 2. So that's degrees of freedom 2. I'm going to copy and paste. And so just like that, if your calculator is a TI-83 or the early TI-84 calculator where it runs strictly as a command like this, then users must complete your own command manually here. So low end is a 16.2. I'm going to put a comma here. And then our upper end is an indefinite upper end. So 1E99. The degrees of freedom is now to be entered after a comma. So degrees of freedom 2. But that now completes our command here. So any version of the calculator now is ready for hitting enter to actually execute our command here to come to the final answer. So let's see how it gives us as a final p-value here. So our p-value right here displayed on the computer screen, on the calculator screen here is a 3.03539 and with an E minus 4. So Now on my writing board, that value anyone have seen on the computer screen means we came to, it's the same as 3.03539 and a lot longer, times 10 to the negative 4. This 10 to the negative 4 over here is the same as the e minus 4 that any viewer has seen back on the calculator screen earlier. And so now it means our final p-value truly is in decimal 0.000030539 and a lot longer. And so now for most of p-values, unless being specified otherwise, I'll stay with 4 decimal places. So 0.0003 as my final p-value for this p-value calculation. And so now once we have had our p-value calculated as the fourth step in the calculation, in the testing hypothesis about independence here, then now we are going to compare our final calculated p-value with a given significance level in a problem. We want to find out whether our p-value is less than the significance level given or greater than. That's what we want to find out, because this comparison will lead us to the decision whether our current sample as a table given here will be giving or showing strong evidence or not. So now let's look back at our wording in the problem given right here. We have, as it's stated here, at significance level 0.001, and again as a reminder, alpha is a symbol for significance level. So we now have a significance level given to be 0.001. So that now means our final calculated p-value is to be compared with 0.001. And so now direct comparison now clearly shows that this p-value that we have calculated falls well below the given significance level. So that now leads to our conclusion saying that the sample, as a table of course, the sample that we have, the sample is an unlikely sample. And being an unlikely sample leads to the further conclusion that the sample we have here as the table itself is strong evidence, or it is showing strong evidence. Strong evidence, or showing strong evidence. For on one hand to say we want to reject h sub 0, because recall now that earlier I was saying the logic of the whole problem here is that we started out by saying that if we accepted h sub 0 to be the truth, if that was accepted, then consequently it produced all of these, but now it led to our final p-value being below the significance level. So it means that the sample we have here is an unlikely sample if we are currently assuming independence. And so now, or another way of saying that once we reject h sub 0, that means we support. It means the same thing, or you can just say only one of the two here. We have strong evidence, the sample is showing strong evidence to support h1. Because now we can support h1 by arguing that political point of view and gender are dependent, meaning there is some kind of relationship going on between the two variables, political point of view and gender, even though we will never point out specifically what the relationship is, because there are so many ways how the two variables can be related. And now ultimately speaking, back on the wording of the question, again, testing a hypothesis will always ask us as a yes or no question. So is the sample showing strong evidence that such and such? And so in that way, now we have just verified that we have strong evidence right in our sample. And so the ultimate answer to the question now is yes, we have strong evidence.